Hello and welcome to this Fabric tutorial about benchmarking Fabric storage. In this video we're going to go over the types of storage available in Fabric, and we're going to do benchmarking tests over different types of storage. This is version 1.0 of the video. We are using FabLib version 1.2.4, and we will try our best to update the videos as the testbed and FabLib evolve. In this tutorial we are going to create a node with an NVMe component, configure the NVMe component for use, and we are going to do benchmarking tests with DD on the regular local storage and on the NVMe component. This tutorial assumes that you already have a Fabric account and have been added to a Fabric project. We also assume that you have the contents of the Fabric config folder set up correctly. To set up the contents of the Fabric config folder and the Fabric RC file, please see the related video. To start, first we need to log in. Then we need to click Jupyter Hub, and then the interface will start. Now we need to find the benchmarking Fabric storage notebook. One way is to use the Start Here notebook. We click Benchmarking Fabric Storage. Another way is to use the File Explorer. So we go Jupyter Examples, Fabric Examples, FabLib API, Benchmarking Storage, Benchmarking Storage. Please note that I am using a slightly modified version of the notebook. Also, please note that we assume that you have the contents of the Fabric config folder set up correctly. For more details, please see the related video. The first thing we need to do is run the top cell. In the top cell, we import the FabLib manager. Then the FabLib manager is available in the variable FabLib. The showConfig function prints the configurations of the Fabric RC file. Then in the next two cells, we reserve the slice containing the VM which has the NVMe component. We will call the slice mySlice. We will select a random site to reserve the VM in. We will call the node Node1. We will give it 4 cores, 32 GB of RAM, and 100 GB of disk space. And we will call the NVMe NVMe1. Then to reserve the slice, we call the new slice function. We give it the name mySlice. Then we call .addNode to add a VM to the slice. We give it the name Node1, 4 cores, 32 GB of RAM, and 100 GB of disk space. Then we use the addComponent function to add the NVMe component. Then we submit. Note that it takes some time to reserve the slice. Here we see that it took around 72 seconds. We can use the getSlice function to get the slice object. It gets the slice by its name. We store it in the slice object. Then we can use the getNode command to get the VM. It gets the VM by its name, and we store it in the variable node. And we can use the getComponent function to get the NVMe component. It gets the NVMe component by its name, and we store it in the variable NVMe1. Fabric provides you with the NVMe component unconfigured. Typically, you would want to partition, format, and mount the NVMe drive in order to use it. You can use the configure NVMe function, and it will do these configurations for you. That's all you need to do to get the NVMe ready for use. Now we can start to do our benchmarkings. We can use the tool DD, short for disk dump, to do our benchmarkings. DD can copy or write data to a location, and it can show us the speed. In order to write data to the regular local storage, we can use, for example, the location temp. Here, we verify that temp belongs to the regular local storage. Since it returns dev VDA1, this means that it belongs to the regular local storage. In order to write data to the NVMe drive, we can use the location m&t NVMe mount. This is where the NVMe drive is mounted by default when using the configure NVMe function. Here we verify that m&t NVMe mount belongs to the NVMe drive. Since it returns this string dev/NVMe, this means that it belongs to the NVMe drive. This is an example DD command that we can use to benchmark either the regular local storage or the NVMe drive. The OOF parameter specifies the location to write to. As discussed, we can use temp output to write to the regular local storage, and we can use m&t NVMe mount output to write to the NVMe drive. The IF parameter specifies what to copy into the new location. dev/0 lets us copy zeros into the new location. The block size parameter specifies how many bytes to write at a time, and the count parameter specifies the number of blocks to write. We can see that benchmarking the regular local storage returns around 40 megabytes, and benchmarking the NVMe drives returns about 350 megabytes. However, this result, though it may seem intuitive, it might not be what we are looking for. The setting might be slightly more complicated than this intuitive result. Here we benchmark the regular local storage, once without setting the output flag to direct, and once with setting the output flag to direct. There is a layer of cache buffers in the way between DD and the regular local storage. DD writes to the cache buffers. The flag tries to skip these file system cache buffers. However, we show that this sometimes produces counterintuitive results. This is because skipping the cache and writing directly to the physical block device is not possible without reconfiguring the FABRIC hypervisor. Therefore, DD writes to the cache buffers and not the device itself. That's why it appears to us as if the I/O speed is very fast. We can run multiple experiments where we vary the block sizes. We note that the maximum block size is limited by the size of the VM's memory. Our VM has 32 gigabytes of memory, so if we try a block size larger than 32 gigabytes, the command fails. We can also vary the number of blocks written. Then we run various experiments with the NVMe drive using various block sizes and various block counts. Here we see that we get the expected results for sufficiently large block size and a large number of blocks. The NVMe outperforms the regular local storage. We can also do a write test followed by a read test. The NVMe outperforms the regular local storage both in read and write. That's it for this tutorial. Thanks for watching.